Timers are fundamental to microcontrollers, and they all typically have several dedicated timer peripherals and other peripherals that require or rely on timers and counters. So the clock frequency of a microcontroller unit can be varied in order to suit the application. So the base frequency that drives the base clock frequency of the microcontroller often comes from an external crystal oscillator, because these give very stable and accurate frequencies. So they don't vary very much with temperature. They're very stable and accurate frequency. So for example, the NXP LPC 1768 embed development board has got a 12 MHz external crystal oscillator. But then before that's fed, before that becomes a base clock frequency of the microcontroller, there's an internal phase lock loops, or PLL. So this is a special type of circuit that used to multiply this base frequency up to a 96 MHz clock frequency. So for this particular board, there's a PLL with a times 8 multiplier. It will multiply up this 12 MHz signal we get from the external crystal to give us our 96 MHz clock frequency, what's used for the microcontroller. So the fact that we've got a high clock frequency, it allows us to have a high resolution. So we consider for a 10 MHz clock, each tick will be 0.1 microsecond. So we know we've got a clock frequency. We've got a clock signal like this, sorry. So we know that this is one period here. So we know that's a period, and we know that the period is just equal to 1 over f. So for a 10 MHz frequency, it gives us a period of 0.1 microseconds. So each tick, so every time the clock signal changes, we get a positive edge. 0.1 microseconds will have elapsed. But suppose we had a 32-bit counter. This is 2 to the 32. So a 32-bit counter can count up to this value, so it can count from 0 up to this. But if each kind of tick of this, so each one of these values is kind of incremented every 0.1 microseconds, this only actually corresponds to less than 430 seconds. So that's not a long time, so it doesn't allow us to time events, like slow events or anything. So the fact that we've got high resolution, it's a positive in the fact that it's very accurate. So a high resolution gives us this very small increment, so we can time very accurately. So with this kind of counter, we could time to an accuracy of 0.1 microseconds, but it negatively affects the range and vice versa. So if you had a lower clock, frequency, each tick will be longer, so it's less accurate, you've got less resolution, it means you can time for a longer period. So very often in microcontrollers we have a prescaler. So this is used to allow the user to modify the clock frequency. We can essentially divide it down and find the best balance for a particular application. So microcontroller peripherals that use timers typically allow the user to select the prescaler value. So this divides down the base clock to a suitable value, and then the user can work out what's the best value for a particular application. So quite often these prescalers are just powers of 2 and just implemented using a counter divider we've seen before. But others can be more complex and allow you to divide it down by any integer value. So we'll look at that previous value. And we had this 430 seconds, for example. That was a 0.1 microsecond resolution. If we actually used the 128 to 1 prescaler, so the actual clock, it will take 128 ticks of the base clock before this other clock will tick. So our resolution will increase by a factor of 128. So it's less accurate. So now we can't measure to every 0.1 microseconds, we can only measure to 12.8 microseconds. But the range has also gone up by a factor of 128. So rather than being 430 seconds, it's now about 55,000 seconds or 15 hours. So this is an example you can see by changing the prescaler, and you can increase the resolution and increase the range. So, depending on what your application is, you can find a specific prescaler value. So microcontrollers typically have several timer modules, and they're often used to measure how much time has elapsed between events. And this is essentially done by counting the number of clock cycles that occur in between events. So this is very useful for many automotive applications, such as measuring the speed of a wheel. So we can get a wheel that's connected to a motor and fitted with an encoder. So the encoder creates pulses as the wheel rotates. So we'll have a series of pulses, and then we might know that a particular encoder creates 100 pulses per revolution. So by counting these 100 pulses, timing how long it takes, we can then work out the RPM, or revolutions per minute, of the wheel. So we'll have a look at an example here. So suppose an encoder outputs 720 pulses per revolution. So we're going to be using a microcontroller with a clock speed of 100 megahertz and a prescale of 100. So this is a prescale of 100 to 1. So we know that this 100 megahertz clock frequency will effectively get divided down to 1 megahertz frequency, what gives us 1 microsecond per clock cycle. So once the timer starts, we count 720 pulses. So we start our timer and we start counting the pulses. Now when the 720 pulses have been counted, we can stop the timer, and the timer's now got a value. Let's say it's got a value of 120,000. So it started at 0, now it's got a value of 120. So the fact that we know it's 1 microsecond per clock cycle, we can just multiply these together to tell us that 0.12 seconds has elapsed. So it's taken 0.12 seconds to do 1 revolution. So we know that in 1 second, we can just divide by that to give us the number of revolutions per second, and multiply that by 60 to give us the RPM. So by counting these pulses and then counting the time, timing how long it takes to get 720 pulses, we can then work out the RPM of the motor. Another very important timer in microcontrollers is a watchdog timer. So microcontrollers and other microprocessors typically have one of these. So this is a timer that enables the computer to recover from a malfunction. So the watchdog timer is based on a counter that constantly increments. Now if the counter overflows, so it gets to the end, so say a 4-bit counter, we know it's going to count 0, 0, 0, 0 up to 1, 1, 1, 1. So once it gets to 1, 1, 1, 1, it'll overflow, and essentially it goes back to 0, 0, 0. So with a watchdog timer, if the counter overflows, this then creates a special signal that resets the computer. So to prevent this from occurring during normal operation, the software must periodically reset this timer before the overflow occurs. So this is often called petting the dog. So you always got your counter counting in the background, the watchdog timer 0, 1, 2, 3, 4, 5, 6, 7, so up to 15 in this example. And if it gets to 15, it'll actually cause the system to reset. So we know that every so often we need to stop it reaching 15, we need to reset it, so it might go 0, 1, 2, 3, 4, reset, 0, 1, 2, 3, 4, reset. So in case of but this is helpful because in case of a software crash or a bug or some error, instead of being reset at 4, for example, 0, 1, 2, 3, 4, instead of the reset occurring, it'll carry on counting, it'll overflow, and then the system will reboot. So this is very useful if you've got a system in an inaccessible place, so if it crashes, you can't just go and fix it. So imagine a space probe or a satellite or something like this. You can't just go and fix it if something happens. So this watchdog timer is just like a simple way of just recovering from some errors. So another application of timers in microcontrollers is in serial communication. So pretty much every single microcontroller has a UART peripheral. So this is known as universal asynchronous receiver transmitter. And this essentially is used to send serial data between devices. So the data is sent one bit at a time. So for example, you might have one device here, and we connect it up to a second device. So I have a transmit line, and so this device can send back. It'll also have a receiver line. So we can send on this line here. We can send ones and zeros. So we can receive them at this second device. So we send the data one bit at a time. But within a UART, you can see from the name asynchronous, there's no clock to keep the communication synchronized. And so in this situation, the receiver and the transmitter must each know how many bits per second are being sent and received. So the very common speeds you see with microcontrollers, 9600, 57, 600, 115, 200 bits per second. So these are very common kind of standard type speeds. So for example, for the 9600 bits per second, the bit period corresponds to 10.4 seconds. So if we wanted to send the value 1010, we'd have a waveform that looked something like this. So on the transmit line, we'd have a 1 and a 0, a 1 and a 0. And because if we set that the baud rate to be 9600, each one of these periods will be 10.4 microseconds. So the receiver knows to read, it'll read the input here, and then 10.4 microseconds it'll read it here, read it here, read it here. So the timers are used to send and receive the bits at the correct time. So another very common peripheral that uses a timer is a pulse width modulation, or PWM peripheral. So we know that microcontrollers mainly deal with discrete digital signals, so we can make an output to be a 1 or a 0. It's possible to turn an LED fully on, so if you make an output of 1, the LED will be on. You make it 0, it'll be off. But if you turn it on and off very quickly, it's essentially flashing the LED very, very quickly. It's possible to essentially create a control signal that enables the brightness of the LED to be controlled. So your eyes can't see the LED flashing. It's flashing too quickly for your eyes to respond. But the fact that it's turning on and off, effectively controls its brightness. So this technique is also very common used to digitally control the speed of motors. And it's known as PWM, or pulse width modulation. This is very common, pretty much all microcontrollers have PWM peripherals. So the output of a PWM waveform is essentially a periodic waveform. So we know the frequency is just given by 1 over this period. And the ratio of the on time to the period is known as a duty cycle. So this will be our, the width, the period of this pulse width. And then this will be the entire period. So for example, we had a 50% duty cycle, the on, so the on time, so we could also call this T on, we could call this T off. So we had a 50% duty cycle, we'd have equal on and off times, and then if you connected that up to an LED, the LED would look like it was at half brightness, and the motor would be running at half speed. So the NXP LPC 17668 microcontroller has got up to 6 PWM outputs. So this is based on a 32-bit timer and counter module with a 32-bit prescaler. So you can control the base frequency of the PWM waveform. So it's controlled by several registers. So by writing values into those registers, you can configure the behavior of the PWM peripheral. So the match register 0, this controls the actual PWM frequency. So in this example here, I'm going to say if the value stored in that register is a 100, we know that the frequency will reset on 100. So in this example here, each as it counts up, this is one period. So after it counts, so this is just the values counting up 1 to 100, and when it gets to 100, it resets it back to 1, and that'll just repeat. So every time it gets to the value stored here, 100, all these waveforms then kind of reset, and the next period starts. The match registers 1 to 7 control to the six different outputs. So, for example, this will be PWM output 1. This might be PWM 2, PWM 3. So the values stored in those registers tell the PWM peripheral when to reset. So effectively, it controls the duty cycle. So you can see here. So for match register 1, if a store value 75 in it, when the counter gets to 75, this PWM output will reset to 0, and again when we get for match register 2, so we've got the second PWM output, when it gets to 50 it will cause it to reset. Match register 3, it will reset on 25. So by controlling the values in these registers, we can control the duty cycle and the overall period, and then based on this actual prescaler, we can control what actually corresponds to in real time, because we can control how long it'll take for each one of these ticks to occur. So another type of clock that's often found inside of a microcontroller is a real-time clock, or RTC. Now this clock can be used to keep track of the real time and date, because the previous timers we've seen, they just count from 0 upwards as long as they're powered. If you turn the power off, the counters will just go back to 0 in most cases. So you can't kind of keep track of time unless you get the devices powered up indefinitely. So the real-time clock modules typically have a 32.768 kHz crystal and a separate power supply. So they often have a coin cell power supply. So even when the actual microcontroller is powered off, there's a separate power supply what keeps power to the real-time clock module, so that can keep track of time even when the main system is turned off. And this is very low power, and the batteries in these last for many years. So you may see them in your motherboard and your PC and so on. You see like kind of coin cell batteries. So real-time clocks use what's called Unix time. So this actually gives the time, keeps track of time, and it's defined as the number of seconds elapsed since the 1st of January 1970. So that's how Unix time works. So for example, Christmas Day in 2016 is given by this value. So this is how many seconds has elapsed since the 1st of January 1970. So traditionally this number is stored using a 32-bit number stored where it's stored in binary. But that actually means that sometime in 2038, so 19th of January 2038, the time in this counter is going to overflow. So it's a 32-bit counter, so it'll be counting up, and it's going to at this time. That timer will overflow. It'll be equal to, there'll be 32 ones, and then it'll overflow and it'll tick back around to 32 zeros. So at that point, instead of becoming 9 seconds here, the timer will actually jump back to this. So before that occurs, systems are going to have to either use a 64-bit Unix time, or else a new epoch will be defined, so they'll change the kind of base date to use. And there's various functions that exist that convert between Unix time and the Gregorian calendar that we normally use. So there's functions we can use what calculate this but convert this number into that date, for example. So we'll look in this microcontroller architecture block diagram. So this is based on the NXP 1768. So you can see we've got the circuit here that generates a clock. So there's going to be various registers there to control the PLL, so we can multiply it up in prescalers and so on. So SPI, that's another type of serial communication interface that requires a clock signal. We've got the real-time clock module, the UART, that requires a timer. I2C is another serial communication protocol that needs a timer. We've actually got a timer module, what we can use to time the duration between events. And we've got PWM as well, so, and inside of the actual ARM core as well, there's also another timer called SysTick. So you can see inside the microcontroller, there's lots of different peripherals that use timers. So timers are very, very important circuits.